The next topic we're going to be looking at is infinite limits. So we touched on this a little bit in a previous section, but we're going to come back to it now and look at it in a lot more detail than we did before. So to start off with, I want to consider this function, f of x is equal to 1 over x. So this is our reciprocal function, and you may recall that this has a vertical asymptote at x equals 0 and a horizontal asymptote at y equals 0. And then this graph has two different branches in quadrant 1 and quadrant 3. And of course, since we have this x in the denominator, our domain excludes x equals 0, which is what gives us that vertical asymptote at x equals 0. All right, now let's start thinking about limits with this. So first I want to think about the limit as x approaches 0 from the left. So as x approaches 0 from the left-hand side, we can see that our y values are going down toward negative infinity. And then as x approaches 0 from the right-hand side, we can see that our y values are going up toward positive infinity. Now, you may recall that when we saw things like this in the past, I told you that when our function approaches positive or negative infinity, the limit does not exist. Now, that's true, but in this section, we're going to be looking at more specifically describing how or why those limits don't exist. So here, for example, think of this as saying the limit as x approaches 0 from the left of f of x does not exist because f of x approaches negative infinity. And the limit as x approaches 0 from the right of f of x does not exist because f of x approaches positive infinity. So it's just describing why the limit doesn't exist and what it's actually doing at that x value. So let's take a look at a couple more examples here. We've got a few more graphs, and we're going to find some left and right hand limits for these graphs. So first we're looking at the limit as x approaches negative 2 from the left from this example here in part A. So if we look at x approaching negative 2 from the left-hand side, we can see that our f of x is approaching negative infinity. And then as x approaches negative 2 from the right-hand side, our f of x is approaching positive infinity. All right. Similarly on this one, we're looking for the limit as x approaches negative 2 from the left. So as x approaches negative 2 from the left, our f of x is approaching negative infinity. And as x approaches negative 2 from the right, f of x is approaching positive infinity. All right, so that's how we find these infinite limits from graphs. Now let's look more at how we find infinite limits from equations. So in order to look at this, I want to start by doing a quick algebra review of finding vertical asymptotes and finding holes from graphs. So let me give you a simple example here. Let's say we have something like f of x is equal to x plus 2 divided by x minus 3. Right, so in order to find vertical asymptotes, you're essentially looking for the restrictions to the domain. So where is the denominator equal to 0? Right, so in this case, we would look at our denominator, and we see that x equals 3 would be our vertical asymptote. Okay. Now, holes on the other hand, let me give you another function. Say we have f of x is equal to x divided by x times the quantity x plus 2. Now this time you'll notice that we have this common factor of x in the numerator and denominator. I'm going to start by canceling that out. Whenever we cancel a common factor, that's what gives us a hole in the graph. So in this case, since we canceled an x, we're going to have a hole at x equals 0. Now let's go ahead and just simplify this function down a little bit more. We'd have 1 over x plus 2, which now from that simplified function, we can see that we still have a factor in the denominator, which is going to give us a vertical asymptote at x equals negative 2. Now in order to find the rest of the hole, We still need a y coordinate to go with this. We would take our x value of 0 and plug it into our simplified function, which would give us 1/2. So our whole is at the point 0, 1/2. All right, so that's our quick reminder of how to find vertical asymptotes and wholes. So let's look at a few more examples of actually applying these to functions. All right, so let's take a look at example 2a here. So in order to find vertical asymptotes and wholes, we first need to completely factor our functions out. In this case, we can factor our denominator as a difference of squares. That's x plus 3 and x minus 3. There's nothing to cancel, which means we'll have two vertical asymptotes from the denominator at x equals -3 and x equals +3. All right, let's take a look at b. So same thing, we're going to start by completely factoring it. There's nothing to do in the numerator on this one, so we'll just factor out our denominator. That's going to be x minus 4 and x plus 1. Again, there's no common factors that cancel, so both factors in the denominator will give us a vertical asymptote. So our vertical asymptotes will be at x equals 4 and x equals -1. All right, lastly, example 2c. Again, start by factoring. This time we can factor both the numerator and the denominator. So our numerator will be x plus 5 times x minus 2. And our denominator is a difference of squares, so x plus 5 and x minus 5. This time we do have a common factor, the x plus 5, so that's going to cancel out, and it's going to give us a whole in the graph at x equals -5. Let's go ahead and keep simplifying our function here. This will simplify down to x minus 2 over x minus 5. And then from the denominator that's left, we get a vertical asymptote at x equals +5. Now to finish finding the whole, we still need a y coordinate. So we're going to take that x value we just found and plug it into our simplified function. And it'll give us -7 over a -10, or 0.7. The whole in this case is at the point -5.7. All right, so that's all algebra stuff. Now let's get back to the calculus. So in order to find these infinite limits, if we can find the vertical asymptotes or we can find the wholes, then we can find the limit. So let's start by looking at example 3 here. We have a rational function, and we want to try and find the limit as x approaches 1 from the left-hand side of this rational function. So just like we were doing above, we're going to start by simplifying this function. So factor it, cancel anything if there's anything to cancel, and then go from there. So let's go ahead and start factoring this. X squared minus 3x over x minus 1. In the numerator, we can pull out an x from everything. Oh, we got our function factored. Okay, in this case, there's nothing to cancel. So what that's telling us is that we have a vertical asymptote at x equals 1. All right, and remember, that's the value that we're looking at here, limit as x approaches 1 from the left-hand side. Since this is a vertical asymptote, that means that this is going to be an infinite limit. So as x approaches 1, it's either going to go up toward positive infinity or down toward negative infinity. In order to figure out if it's a positive or a negative, we're just going to make a little table, plug in some points, and see what our y values appear to be approaching. So since we're looking at the limit as x approaches 1 from the left, I went ahead and I just picked a few x values here just to the left of 1. And I plugged these in ahead of time, and I ended up with 6.75, 18.9, and 198 0.99. All right, and of course at 1 itself, we know we have this vertical asymptote. So we can see then as x is approaching 1 from the left-hand side, our y values are starting to approach positive infinity. All right, now let's look at that same function, but this time we're looking at the limit as x approaches 1 from the right-hand side. Again, we know that that's a vertical asymptote at x equals 1. So this time I just picked a few values to the right of 1. And again, I went ahead and plugged these in ahead of time. And what I found was negative 200.99, negative 20.9, and negative 8.75. So this time, as x approaches 1 from the right-hand side, we can see that f of x is approaching negative infinity. All right, let's look at another example. So same as before, we're going to start by completely factoring this function. All right, so the numerator, we can factor this as x plus 4 times x minus 2. And the denominator, we can factor this as x plus 2 and x minus 2. So we have a common factor here of x minus 2 on the top and the bottom. That can cancel out, which leaves us with x plus 4 over x plus 2. Now in this case, the only value we actually care about is x equals negative 2, more specifically around x equals negative 2. And we can see from our simplified function that we're going to have a vertical asymptote at x equals negative 2. All right, so this is again going to be an infinite limit. It's either going to be going up toward positive infinity or down toward negative infinity. So I again just picked a few values here just to the left of negative 2, and we're going to go ahead and plug those into our function. All right, so when I plugged these in, what I got was negative 7, negative 19, and negative 199. So since all of our values are negative here, we can see that as x approaches negative 2 from the left-hand side, f of x is approaching negative infinity. All right, now looking at our right-hand limit now, still have the same function. We still know that we have a vertical asymptote at x equals negative 2. We're just looking at values to the right of negative 2 this time. So again, just plugging those in, I ended up with 201, 21, and 9. So since they're all positive, we can see that as x is approaching negative 2 from the right-hand side, f of x is approaching positive infinity. All right, one more rational function. Let's again go ahead and start by factoring this. So this time we can factor out our numerator as x plus 4 times x minus 3. And we, of course, have this common factor, x minus 3, that we can cancel out. And that is, of course, telling us that we have a hole at the point x equals 3. All right, so if we simplify our function down then, we're just left with x plus 4. All right, so we know from what we did in a previous section looking at indeterminate forms that if we're able to simplify a function down and we can then plug our c value directly into that function, then the limits are going to be the same. In this case, the limit that we're looking for, limit as x approaches 3, the 3 value is a hole this time and not a vertical asymptote. So it's not an infinite limit this time. We're actually going to get a number out of it. So we can see here that our limit as x approaches 3 of the original function is going to be equal to the limit as x approaches 3 of our simplified function, x plus 4. And then if we just plug that in, 3 plus 4 is equal to 7. So our limit is 7. All right, let's look at a couple functions that are a little bit different. So not just plain old rational functions, but some trig functions in here and a little bit of variety for us. So this next one, we do actually have another rational function, but with some transformations added onto it. So this time we're looking for the limit as x approaches 0 from the right-hand side of 1 plus 1 over x squared. All right, so this time, this is a little bit different. I'm actually going to go ahead and just start by making my table right from the get-go here. So we're looking at approaching 0 from the right-hand side. So I went ahead and picked a few values to the right of 0, and I'm just going to go ahead and plug them into my function. So if we plug in 0.01, we get 10,001, and then we get 101 and 17. So we can clearly see by looking at this, as x approaches 0 from the right-hand side, our y values are starting to approach positive infinity. All right, and then one more here, we're going to look at a tangent function. So in this case, looking at the limit as tangent approaches pi over 2 from the left-hand side of the tangent of x. All right, so pi over 2 is approximately 1.571. So I just picked a few values to the left of that again, and all we're going to do is just plug those into our function and see what we appear to be approaching. All right, so if we plug these in here, we're going to get 48.1, 92.6, and 256. Again, we can see that as our x values are approaching pi over 2 from the left-hand side, our y values are getting bigger and they're getting positive, so they're going to be approaching positive infinity. All right, you'll see a few more examples if you look at the notes that I posted, but that's all for our video today.